Good afternoon, ladies and gentlemen. It's lovely to see you all here. And welcome to the Geological Society of London and to this, the 9th 2015 Society London Lecture, which is entitled Landscape Dynamics, Erosion and Sedimentation. My name's Nick Billam. I'm Director of Policy and Communications here at the Geological Society. And it's my great pleasure this afternoon to welcome today's speaker, Dr. Alex Whitaker of Imperial College, London. Now, before I carry on, I've got a little housekeeping note aimed particularly at regular attendees at our lectures. We love having you here, and we love your enthusiasm. We have a full room almost every time. In your keenness to arrive, some people are arriving very early for the lectures, and so I've been asked to say if you would make sure that you arrive no sooner than 2:30 for the 3 o'clock lecture, no sooner than 5:30 for the 6 o'clock lecture. That will just really help us in terms of our staffing, because we have often other events going on and my colleagues aren't necessarily ready to receive you on your arrival if you're much earlier than that. So we're very grateful to you for your cooperation with that. Now, the sedimentary record is controlled by sediment routing systems, which transfer sediment from their upland source catchments to depositional sinks. To decode the stratigraphic archives that these sediments create, we need to understand the behaviour, response and sensitivity of sediment routing systems to both tectonics and to climate. Today's talk will explore how come we have come in addressing this really huge challenge. Our speaker, Alex Whitaker, read natural sciences at Cambridge before moving to Edinburgh University to do a PhD in landscape dynamics and active tectonics. Following an Entente Cordiale fellowship at Université Joseph Fourier in Grenoble, Alex moved to Imperial College London to work with Professor Philip Allen on sediment routing system dynamics. He was appointed lecturer at Imperial in 2010 and senior lecturer in 2014. Alex received the Chorley Medal from the British Society for Geomorphology in 2008 and the President's Award of the Geological Society in 2009. And in 2013, he was awarded the President's Medal from Imperial College for his field teaching. Ladies and gentlemen, please join me in welcoming Dr. Alex Whitaker.
Great. Thank you very much, Nick, for that very warm welcome. And it's a pleasure to see so many people here. So, landscape dynamics, erosion and sedimentation. Now, this is a deliberately broad title, and the first thing I want to do actually is to thank all of the colleagues and students who I've worked with over the years, of whose names are listed here. So this isn't just my work, it also reflects some of the ideas and discussions and field trips I've had with these people. So I want to start with a picture that's close to my heart. This is the Fiumignano fault in central Italy. The fault slips at something like 1.2 millimeters a year, and this giant bedrock scarp has been entirely created since the early Holocene. And in fact, nowadays people are actually studying the rate of slip of this in terms of individual earthquakes using cosmogenic nuclide analysis, and this is this scar along here. But I want to ask a broader question. How does an active fault like this influence over the long time scale the topography of our planet? And what does that mean for the sourcing and routing of sediment from uplands to depositional stratigraphy? So if we zoom out, it's fairly obvious to see. Here's the fault. It runs all the way along here, and it's uplifting this large limestone massif. We've got a channel running through here that is sourcing sediment. If we studied the morphology of this channel, or indeed the sediment it's producing, can we learn anything at all about the rate of movement of this fault? Or if I zoomed out now, so I'm going big, this is Tibet, Nepal, and we can see the Ganges, Brahmaputra, and the Bengal fans. This is an image from the shuttle. So this system exports something like 1 billion tons of sediment to the oceans every year. To what extent are the sediments that we find here on the plain or off the shore, to what extent do they represent tectonic and climatic processes going on here? You know, we could ask some really important thought questions, and I'm going to put these questions first because I think they're questions to which we would love to know the answer, but currently we don't have them. Are landscapes twice as steep if fault uplift rates are twice as big? If I make my climate, say over this mountain belt, instantaneously twice as wet, do I get twice as much sediment eroded out? And even if that occurs, could those effects be detected in the sedimentary record? These questions are fundamental because they go to the heart of what we do as geologists. So I want to see and explore the extent to which we can answer these. Now, some people think they already have the answer to this. A colleague of mine, Eric Kirby, along with Callan and Nathan, they published a paper in Nature a couple of years ago where they basically argued that topography can be used directly to reveal seismic hazard, and they demonstrated or claimed to demonstrate that after the Sichuan earthquake, you could see that there was a big fault there from the geomorphology of that region. Similarly, Brady Foreman, he's a really clever dude, he argued that that this big sandstone massif in Colorado, that was generated by the Paleo-Eocene thermal maximum, which we know was a very short transient spike in terms of temperature and probably also rainfall. So these papers argue for a one-to-one link between boundary conditions and landscape response. One might ask the question, is this wishful thinking? You know, how simple is this? Now, you know, the people who like the world simple, and I suppose I am one of them, would say that on the gross scale, when we look at Earth surface processes on planet Earth, it is relatively simple in a philosophical sense. The boundary conditions that we're all interested in are tectonics. That tends to send stuff upright. And then we've got climate. That tends to promote erosion. Those two factors interact to influence the landscape shape, the geomorphology, if you like, and we can describe that quantitatively nowadays. And indeed, the sediment release from some uplifting source area. And that sediment release, whether in terms of grain size or volumes of sediment per unit time, that's going to be transported down the system and then finally extracted into stratigraphy. You know, so this kind of linkage is simple to explain. And I think it's clear that both geomorphic metrics and the nature of sediment deposits in basins should depend on first-order variations in tectonics and climate. You know, in a general argument, that seems to hold, should hold. So that leads us to what one might term the holy grail of sedimentologists and stratigraphers. Or you might say solving the inverse problem. Can we do predictive stratigraphy on the basis of tectonics and climate? Can we quantitatively invert the landscape and the sedimentary record for forcing factors? That would be nice. You know, we'd get plenty of nature papers if we could do this every day. I would argue, and I think we should be aware of this, that there are some problems, and I want to explore what those problems are and the kind of work that's being done to address them. So, you know, what are our spanners in the works? Well, I'm going to introduce 4 of them. You guys may well have others that you've got in mind. I presented to you just now a very complicated or very simple diagram of a sediment routing system. But in fact, in reality, they are complex. I've taken this diagram from my colleague Philip Allen, and this shows all or a range of the different processes that go on in a landscape. We might be talking about hill slopes and channels, landsliding, some kind of sediment transport within rivers, some kind of buffering on the floodplain, and then we have to remove that sediment offshore. Or we could think about it as a state of the sediment lying in a range of states that are coupled, and we have transfers between them. We actually don't know how sensitive these different systems are to perturbation. We don't know how many of these processes we really need to worry about. Presumably, if we're thinking about long-term landscape evolution, do we need to model every landslide? You know, that sounds impossible to me, so hopefully that we don't have to do that. And of course, we need to think about how they interact together. So what level of complexity is the correct one to approach this problem? I think we also have to think about how sediment routing systems and stratigraphy, or surface fluxes and stratigraphy, are fundamentally not the same thing. Now, this is the Collegat conglomerate in the Spanish Pyrenees. I take my undergraduate students here every year because it's amazing. Beautiful unconformity. This is one sediment routing system. This pink stuff, the Montsor, is interfingering with it. And you can go and have a look at these sediments. They look great. These are fanglomerates. They're stream flow dominated. And you're like, oh, yeah, I can measure this. You know, this is basically what was coming off the mountain at the time. The trouble is that what you find deposited in stratigraphy is not and never was the same as the surface flux from which it came. Let me put that in a different way. The sediment characteristics preserved in stratigraphy are usually not the same characteristics as in the surface. Well, how might that work? Well, we know that, let's say we have a particular distribution of grain size in the supply. This is a frequency, probability, if you like. This is grain size from fine to coarse. If this is the surface flux, stratigraphy, or into stratigraphy, we extract a proportion of that, usually something coarser. So that means what we find deposited geologically is not the same as what passed over the top. And I think that we need to understand and accept the transfer function between surface fluxes and what we find deposited. And that's a big challenge for us. This problem isn't so bad if we have a bottomless pit into which we are chucking sediment. You know, if, for example, fault slip rates in a normal fault boundary basin are high. But it is quite acute when accommodation generation is small compared to the surface fluxes. Right, let's go on with our tale of woe. Now, timescales, rates, and dates. This is an interesting paper published by a colleague of mine, Antoine Vernon, in geology. He's a smart dude. And what they were basically arguing in this paper is that this is the Alps, and we've got things like relief, precipitation, rock uplift rates, exhumation, bedrock exhumation from apatite fission track constraints. And one of the comparisons that's made in this paper is that zones of apparently high rock uplift rate, shown here, and in the fission track exhumation ages, could be matched to some extent with zones in red here of high precipitation. Does that therefore mean that precipitation is driving, or increased rainfall is driving rock uplift rates, or indeed is the causation the other way around? Well, we don't know the answer to that question, but there's a more fundamental problem, which is that this and this are averaged over geological time periods. We're talking averaging over millions of years, tens of millions of years, right? Even longer. this box, is a product of averaging over the last 50 or 60 years. So we're almost trying to compare an apple with an orange in terms of timescale. And actually knowing about timescales in terms of climate, which are meaningful in terms of the geologic record, is really hard. So let's come on to that. What we might term the problem of knowability. There are lots of factors we'd love to know in the geologic past. Let me name some: vegetation, discharge histories, storminess, etc. Now, it would be nice to know everything about sediment sourcing in a particular catchment or particular storm tracks. But it's quite clear to me that we are never going to know all of those details in the geologic past. So if we believe that to understand landscape dynamics and sediment routing over geologically relevant periods, let's say 1 million years, I need to know about the time-integrated history of discharge or storminess in a study catchment or a mountain range. Well, perhaps that's job done. I mean, we might not be able to get there. So let me ask the question: what is the right level of complexity to quantify and model sediment routing system dynamics? Well, I would say that if we think that the right level of complexity to model this involves knowing about all of these things that are fundamentally unknowable, then I think I'm going to stop this lecture here. We may as well go home. And then that's job done. We just can't do this. This is probably the attitude that one would take if one was a physicist. But you can't help some people. So instead, as geologists, we actually have made progress. And I would actually say that landscape response to tectonics has been relatively well studied in the last 15 years, and we've learned quite a bit. So that's positive. In particular, I think the response of tectonically driven systems to faulting and uplift is something that we now understand relatively well. So this is a compilation that a colleague of mine, Eric Kirby, put together. Again, with this Kellen Whipple dude, he was the one who was involved with the Nature papers showing that earthquakes could be basically detected from geomorphology. And what he is plotting here are normalized steepness indices. Now, let me translate that into English for you. This is just river channel steepness, but normalized by a measure of drainage area because rivers are less steep when the drainage area is big. So it's actually, this is quite simple to work out. Just think about it as channel steepness against a measure of basin averaged erosion rate. It might be derived by cosmogenic constraints. There's a range of ways of doing that. And these are for landscapes that we think are in tectonic steady state. So this is actually driven by tectonics. And what he largely argued was that landscapes are steeper when tectonically driven erosion rates are big. So that's useful. And actually, when you do the maths of this, and I'm not going to run through all of the maths today in this kind of talk, then I might even go a little bit further and say that these channels are predictably steeper if you use something like a stream power driven erosion law when tectonically driven erosion rates are high. So there is some quite well behaved geomorphic observations here. Similarly, and this is some work that one of my PhD students, Mitch Darcy, had done, he looked at a whole bunch of landscapes where we had good constraints on the tectonics. We knew what the fault slip rates were, and we wanted to ask that question in reverse. If we know what the fault slip rates are, and we compare, for example, areas with similar rates, but with different climates, do they actually have different geomorphology? Are those landscapes steeper or not so steep? That's a quite a good way to approach, and we went all the way around from Idaho, California, Baja, California, down in the Andes. I flew back from here on Sunday. It's an amazing place. And we actually got a similar but predictable result. And this is kind of handy as well. So for areas with a similar uplift rate of order 1 millimetre a year. This doesn't sound very much, but that's a kilometre of topography rate in a million years. Then we find that channels are less steep as the rainfall rates go up. And that's in a predictable way. And in fact, the dependency on here is something like the square root of drainage area. And that is again, or the square root of precipitation. And that is again what one would predict from a set of relatively simple landscape erosion laws. So that's good. We've got some idea that at least in areas which are roughly in tectonic steady state, that we can relate bulk climate or tectonic constraints to the shape of the landscape. Now, of course, we might be more interested, if we're interested in, for example, in the generation of sediment, to think about how does the landscape respond to a change in a boundary condition. For instance, a change in fault slip rate. Well, looking at landscape or sediment routing system response to a change in one of these conditions typically requires us to do some modelling. That's because when we go into the field, and I love going into the field, but we get a snapshot. And I want to get some constraints on evolution over time. And for that, I turn to numerical modelling. I did this work actually with a colleague of mine, Michael et al. He's very clever. So we built a catchment model in a code called child, and we put in a fault, scaled actually to the fault I showed you at the beginning of this talk. And then I'm just going to increase the slip rate on here from by a factor of 3 up to about 1 millimetre a year, a bit more. Now, we've used a stream power erosion law. You don't need to worry about what these exponents are. There are people in the world who do, but I don't think we should dally about that. So, let's actually explore some of these. What do we get if I take a river profile? And actually, in the end, we need to worry about rivers. I'm interested in rivers because they're the main means by which tectonic and climatic boundary conditions are transmitted to the landscape. They set hill slope, they set the boundary conditions for hill slopes, and then they export that sediment. So if we don't understand what rivers do, we're going to get nowhere in terms of understanding surface process response to tectonics and climate. So here's our fault, and we're going to increase the slip rate on this fault and have a look at the river long profile. This is the elevation of the channel against distance. In this case, I'm plotting upstream distance from the fault, which is pinned at the origin. So as we do this, and you can look at how the topography changes up here, we develop what you might term a nick point or nick zone as a wave of incision propagates up this channel until actually the headwaters start to be cut off. So we've got a very steep channel. This is in model time about 0.6 million years. And this wave of incision continues until we end up with a channel that is steeper all the way through so that it can keep pace with our newly imposed uplift rate. And so this is the height of the nick point. And this is the difference in flow rate between what we started with and what we ended up with. I did a factor of 3. So actually, we could go to real landscapes and say, well, let's actually measure some nick point heights, compare them with fault slip rates. Do they actually correlate? The answer is yes, they do. So this modeling has given some inspiration to say, well, we have an idea about how these channels should behave. What do we actually see when we go to real landscapes? Because, as some of you might know, modeling can be a bit like a black box. You get in what you get out what you put in. Some people don't like to look at real geology because it pollutes the simplicity of their lovely model. But I'm not one of those people, so we could go into the field and actually have a look. So this again is the Fiumicino fault. I showed you at the beginning of this talk the fault over here. It cuts across this river. It's called the Rio Torto. What's nice about this actually, it does have big profile convexity and elevation against downstream distance. This is the nick point. upstream of the fault. And we can actually work out how big is the incised area associated with this nick point that is apparently moving upstream of this fault, that we know from geologic constraints increased its slip rate by a factor of 3 in the middle of the Pleistocene. So we can go to this area and we can go to the top. That's up here, right? It's very nice. It's very pastoral up here. It's got beautiful wide open valleys. This is really not going for it. It's not incising too much. Go down here into the incised part of the gorge, and this river is really cutting down fast to keep pace with the fault. And all of the sediment that's coming out of this catchment is really coming from here. So I would say that landscape response to active faulting is relatively well constrained in terms of field data sets. If I went to another couple of faults in Italy as well, this is a Ficino fault. This slips at 2 millimeters a year. This is really fast. It's the fastest slipping fault in the Apennines. Again, their river long profiles do exactly what these numerical models suggest with the big convexities. And again, they have these nick points that have got a lot of green dots in. Those green dots are landslides. Well, why does that matter? Because not only are we exporting all of the sediment from this area, but as geologists, we are interested not only in the volumes of material we remove, but also the grain size of that material too. And this is the grain size of material in transport. And you can see in the grey box, that's the incised region here. So the sediment there's more sediment coming out, and it is coarser. So we've got median grain size, that's in white. The black ones are coarse fraction grain size. So I would say that for catchments eroding active faults, grain size and volume change are coupled. And that effect is driven by steeper slopes and landsliding. So I've talked a little bit about how the landscape responds, but I sold this talk in terms of thinking about how that might influence stratigraphy. So again, we need to talk to modeling people. And I particularly work with this dude, John Armitage. He is a physicist, but he's tame. And he put together a really smart model for us where we basically coupled a catchment system to a small-scale alluvial fan. And then we wanted to say, well, here's our idealized simple sediment routing system. How does it behave when I perturb it by tectonics, or as we'll come on to, climate? So we can parameterize the catchment erosion. This is a nonlinear diffusion law. I don't think you need to worry about what it does. This basically tells you how much stuff you're going to erode off. If you're interested in that, come and find me. We've coupled it to grain size release that I've shown you from field observables in Italy. We can take the catchment basin tectonics and scale it to an appropriate setting. And in the hanging wall of the normal fault, the extensional fault, we can deposit using a mass balance approach. And we find the grain size using a self-similarity model that Chris Powler actually introduced to start with. So we could do all of these things, which is kind of cool. Let's actually have a look at some colorful pictures. So what do we get for one of these systems if we, for example, double the fault slip rate? Now, for simplicity here, I'm just going to show you the basin stratigraphy, right? This is the thickness of the basin sediments. This is distance away from the fault. The fault is here. The catchment is like over here. I'm not showing you that. We run the model to a steady state. So that's where this sediment flux goes off. And then at around 5 million years, we perturb the system by a factor of 2. And the response of the stratigraphy to that, that's in here, right, is a stepping back of stratigraphy. So it gets slightly finer. And the reason for that is that we create our accommodation space instantaneously when we increase the fault slip rate, but it takes time for the landscape to respond. And I've shown you some of that from field data observations. Similarly, and this is interesting, if we do the reverse, in this case, I am going to decrease the fault slip rate. Then we get the progradation of this coarse green, that's quite coarse, right? Coarse gravel wedge out into the basin. And again, the reason for that is that we've instantaneously halved the generation of tectonic accommodation in this basin, but it takes time for the landscape to realize it ought to be eroding much less rapidly because the tectonic slip rate has gone down. So that's kind of neat. And actually, we can then scale this to actually field data that we collected. So again, this is in the basin. Thickness of sediments goes down to 4 kilometers thickness, distance away from the fault, which is here. And this is coarse fraction grain size. The grain size goes up when the fault slip rate increases, and that's exactly what we've observed from field data. And then, you know, that decays over time. Now, what I want, the change that we've imposed is here in this stratigraphy. And I want you to have a look at boreholes, theoretical boreholes, through stratigraphy at point A and B. And this is A and B shown on the right-hand side here. And what you can see actually is that at borehole A, that's this one, at the time of my slip rate increase, and this is for a factor of 2, we get a coarsening of stratigraphy in the basin. Yet further downstream on the same timeline, we get a fining of stratigraphy, or the grain size in stratigraphy. So this means it's complicated, right? That the coarsening is due to the fact that when a landscape responds to an active fault, we tend to get an erosional wave, and we get coarse sediment being generated. But we get a fining effect further down in the basin because the grain size fining rate is very rapid, and that's because we've generated a large amount of accommodation, and we don't have enough sediment to fill it. So these effects, you know, in the same timeline really start to challenge how we go about correlating stratigraphy. And they also suggest to me that although it's tempting to go up to an exposure, you see some gravel, we wave our hands and start talking about high energy environments, we could, you know, do better. What does this imply for geological sediment routing systems? Well, I've just shown you very simple models, but as a field geologist, I'm always interested in looking at real examples. So, we're jumping around Europe at the moment, and I want to take you to the Spanish Pyrenees. This is a lovely place to work. The geology is incredible. There's excellent wine. I highly recommend it. So I'm going to focus here in the south central unit of the Spanish Pyrenees. There's Tremp. Barcelona is down here. And we're going to look at this blue box here, and particularly we're going to look at Eocene stratigraphy that is, let's say, between 40 and 30 million years old. And this is the stratigraphy we're looking at. This is a map of stratigraphy of that age. And at one stage, these stratigraphic units were actually joined up. There are bits around here that we don't see anymore because they've been eroded away. Now, what my student, Nicholas, worked on, and this is in conjunction with Philip Allen, was to say, how is this Paleo sediment routing system, this old sediment routing system, responded to a known change in tectonics? So, what is this known change in tectonics? Well, these are exhumation rates in the Pyrenees that we have got from fission track data from cobbles and also from bedrock. These are apatite fission tracks. So this is a method of working out how fast material has been exhumed, eroded to the surface. You know, so if you want to know more about the method, come and speak to me. But what we know is that when the center, the axial zone of the Pyrenees was exhumed, say around 35 million years ago, there's a big increase in exhumation rates, tectonic rates, in the center of the mountain belt. So we wanted to ask the question, this is a good question, how is that expressed in well-constrained stratigraphy? We've got a good idea of what we should expect from models and theoretical reasoning, but what do we actually see? Well, let's go on and have a look at that. It's an amazing place. These are the GURP conglomerates. This is the feeder systems to this sediment routing system. Now, this is really impressive to look at, right? You look at this and you look at this mountain, and you're like, whoa, this is quite good. There's a lovely little restaurant here. If you're ever there, I totally recommend it. But even better than that is the geology. And it's forming this big hill. But in fact, this hill is made of conglomerates, and this wasn't a hill at the time. This is actually a paleo valley that has been filled up with conglomerates that are difficult to erode, and therefore they are standing proud now. And my student Nicholas spent a very long time correlating stratigraphic sections all the way through this stratigraphy of the same age to join up this sediment routing system. This course over here, I showed you a picture of this, and it goes out all the way out to the Einser and then finally the Hacker Basin. And we've actually got paleomag constraints and a bunch of and we've also looked at provenance, heavy minerals. There's lots of ways of joining up sediment routing systems. But we're basically going to talk about 3 timelines that are around 40 million years, around, let's say, 37, 36 million years, and then, let's say, 34 million years. And I want to say, well, how much stuff has been eroded per timeline? And what Nicholas did was actually a lot of field work to look at the fraction of conglomerate sandstones and then siltstones and mudstones that are within this geologic system. So we're actually able to reconstruct what we might call the sediment fairway. This is where the stratigraphy was at the time. So that's this outline here, and we also have seismic data to back this up. And you know, we could be like, well, let's measure this really carefully. How much stuff is in here? It's a good question. What's the volume of material we've eroded? Well, we did a lot of cross sections. Nicholas and Philip did a lot of working out. The errors are probably a factor of 2, but it's a lot better than knowing nothing. And we then said, well, let's actually plot what we get out of these systems. How does the fraction of conglomerate and sandstone and mud, this is timeline 1, vary down system in this kind of geologic routing system? And this is before the tectonic change. So we get a lot of conglomerate near the source, and then it decays to practically 0 by 100 kilometers down system. And then we get dominated by silts and muds out towards the Einser Basin. And if you sum all of this with respect to the volume, you get the total grain size fractions that have been eroded. I don't know whether any of you have ever wondered. I ended up thinking about this in the shower one day. What is the overall grain size distribution that gets eroded from a mountain belt over time? Yeah, it's a good question. Well, here's the answer, right? This is the distribution of sands, conglomerates, silts, and muds. So this should make the Geological Society happy, because this year is the year of mud. And this mountain belt was producing 66% silt and mud at 40 million years ago. How does that change over time? That's a good question. So this is the percentage against downstream distance. So actually, at the time of the change in time interval 2, we are eroding some more. We've got a greater depositional volume. But the instantaneous change actually is that, if anything, we've actually got a little bit more mud coming off. And then by the time we get to 34 million years, this is like 2 million years after our tectonic change, we end up with this configuration where we've increased the percentage of coarse stuff that we're exporting, and we've decreased the percentage of mud. So there is a time delay in the grain size fractions that's actually at a different rate from the overall increase in depositional sediment volumes. So, during a threefold tectonic change from, say, 0.25 to 1 millimeter a year, we get this kind of change in the overall grain size distribution eroded from a mountain belt. And I think that's important to know these kind of numbers, and I think that they are significant. So, I think it's the grain size distribution and its partitioning evolved downstream. So what we actually have been able to do is to actually even work out where, these are just little schematic diagrams of this system, where does that sediment evolve to? Where does it go over time? Where is it stored? And I think that's important, if you want to, my colleagues in industry often ask me, well, tell me about where the sands are, how much of them are there? So we've been able to reassure them about how much they might expect in a bunch of sediment routing systems, because a lot of people go to Einsa, because it's charming, and they have great geology to look at turbidite systems there. Now, I think what we learn from this is that tectonic control on sediment release really matters. But what I haven't talked about is climate. That's because it's harder. And the danger with climate is that it gets shredded in our sediment routing system. Because we know, for example, in the last 1 million years, we've had 10 glacial interglacial cycles. But we also know that, at least from our tectonic studies, that landscapes can take of order 1 million years to respond to a tectonic boundary condition change. So what happens to landscapes when you start to perturb them an order of magnitude more rapidly? Well, we can use the same model again. And what I'm going to do here is just make it rainier. I'm going to double the rainfall on this system and see what we get. I've left the tectonics alone. Now, this is sediment flux over time. So we run up to a steady state, and then I'm going to make it rainier. So the instantaneous effect of that is to generate more sediment. And that's because it's wetter, and we still got steep catchment slopes. And we get coarser grain sizes as well, and there are good hydrodynamic reasons for that. And the stratigraphic result is clear, right? We get this big spike of sediment that's eroded out into our theoretical depositional basin. That's kind of neat. And actually, it's this kind of effect that Brady Foreman, I talked about his work at the beginning of this talk, has used to argue that the Paleo-Eocene thermal maximum might have eroded this material. So we get this transient spike, but this is just for a step change in climate. What we actually know is that climate has gone up and down with 100,000 year periodicity in the last million years. This is an example of a model just with a 400,000 year periodicity, and that's just so that because it's easier for you to see, where we're varying the rainfall from 1 to 2 millimeters a year. Up, down, up, down, up, down, up, down, up, down, up, down. And again, I want you to ask the question, well, what do we see in our stratigraphic units? The catchment is over here again, right? This is our basin. The change happened here. Well, when we first initiate this change, we do export lots of coarse sediment to our basin. But then that signal gets damped over time. We start to lose it. And that's because so again, this is time and the sediment that's coming out. So it goes up and then it just sort of dies away. So in here, right, the boundary condition change in here is the same as over here. It's just when, but after a few million years after the change, the catchment is really buffered to the system. So when this time change, when this changing precipitation signal occurs, really matters. And we see the same in the mean grain size that's exported. So if I were being unkind about some of my oceanography colleagues, one might ask the question whether or not we're being naive in attempting to match what you might term climate wiggles to stratigraphy. Well, having said that, There are lots of people who believe we can. And I think, if we're going to solve this question in terms of looking at physical characteristics of stratigraphy, we actually could do with some evidence. That always helps. So, yeah, some field data. I like that. We might also want simple sediment routing systems, then we understand what's going on. It would be nice to have a place where we can close the sediment budget, where we know what the lithologies and tectonics are doing. We've got rapid accommodation generation, so we don't have this selective transfer function problem I told you about. We'd like to have really high temporal resolution of stratigraphic dating. That would be lovely. And we'd also like to know what the paleoclimate was as best as we can. This is quite a shopping list. However, we think we found a place where we can actually investigate this problem. And this is in Owens Valley in the US. It's a really amazing place to do. And I should say that the work I'm talking about here is new exciting work that my student of mine, Mitch Darcy, has done. He's just finished his PhD. He's very clever too. And he has demonstrated that we've got quite constant tectonics along here. We know what the bedrock is. We have amazing climate history from pluvial lake records. It was quite wet here in the last glacial maximum. We know what sea surface temperatures are off the coast of Santa Barbara. We've got data of moraines. We've got delta 18O cores. And this is good. This alluvial fan stratigraphy is dated by 89 exposure age estimates, which we've got from beryllium 10 exposure age estimation techniques. So what does it look like, guys? So I've just taken this from Google Earth. Here's the Sierra Nevada. These are these alluvial fans, and this is the lovely town of Independence. So the fault runs along here. And just here is what I have labeled the terrifying correctional facility. This is the youth detention center they have for the county. It has a particularly interesting function that you might be interested in. Inyo County Jail. I particularly enjoyed the find inmates of this facility. So if there's someone you think is locked up there, you know where to search. Anyway, we did not go down that route and instead went to have a look at the fans that lie just up here, which are great. So, when you go here and you look at them, they actually have lots of different stratigraphic horizons. That's nice. And because of the dates that I told you about, we know that, for example, this is 120,000 years old. All of this sediment is on around 30,000 years old. This is the 6,000-year-old surface, and the modern system is down here. And I want to ask the question, is the stratigraphy, the grain size of the material in here, does that demonstrably change over time? Well, we did a whole bunch of stuff to answer this question, including mapping of what the fans are like, because you need to know that. We did like 292 localities. There's a lot of work that's gone into this. We did a lot of grain size analysis. Measuring grains is an art in itself. The data here is coming from something like 30,000 class counts. Mitch tells me proudly that he has done more than 100,000 during his PhD, but as I suggested to him that practice makes perfect, so that's always a good one. And then finally, we wanted to compare with some paleoclimate records. And I picked two. These are ODP sea surface temperature records. This is from Santa Barbara. And this is a Devil's Hole delta 18O record. This is from a speleothem in a cave. And they largely correlate, right? So if we actually zoomed out and had a look at that, then we've got particular surfaces that are well dated. These black dots are all of the data I'm talking about. And they're all from near the apex of the fan. We have constrained the downstream finding rate. And it's not very much, so we're not going to worry about it for the data here. So I think the first thing I want to point out to you is that blue are surfaces and stratigraphy that are glacial in age, and red are the ones from the interglacial, either the current Holocene or the last interglacial. You can see that they have demonstrably different grain sizes, and just in the next few slides, I'm going to talk about D50, the median grain size, and I'm going to talk about D84. That's the coarse fraction grain size, the 84th percentile, on this cumulative grain size frequency curve. So that's 100%, and this is the particle diameter. Right, so here's our climate record. That's nice. And I showed you the correlation with sea surface temperatures before. What you need to know is that when this number is high, we're talking about conditions in the interglacials. That's perhaps a temperature today of around mean temperature of 16 degrees, 200 millimeters a year rainfall. Down here, in the last glacial maximum, the whole glacial period, we're talking about 5 to 10 degrees cooler, 2 to 4 times wetter. So that's nice because we've got a measurable change in what the climate is like. So let's actually have a look at how the grain size compares. So this is the median grain size here, and these are our average measurement for our channels, which in this case are debris flow dominated. So we can see that the grain size, it gets fine during the last glacial maximum, which is around 20,000 years or so, up to, there's a bit of a warming around 80. And if I put the data behind that, these are the individual measurements. And then I'm just going to put on, because these are debris flow dominated, we can also measure the levees of these channels. And they do a similar thing, right? So let's put on the data behind it, right? I hope that you can see that the grain size that's exported shows a really nice correlation with our paleoclimate proxies. And I could do the same if I put on the coarse fraction grain size, the D84, right? So it's coarse in the Holocene and in the last interglacial, and it's fine during the glacial periods. So this was, it's been interesting and exciting for us because what we're seeing is that grain size is recording climate with really good fidelity, and this is the sort of head turner, right? We're actually getting coarser grain sizes exported today, even though it is drier and it is warmer. And the grain size is finer when it's cold but wet. The response time is less than 10,000 years. So, how can we generate that? Well, we thought about sediment sourcing effects, storm sizes, potentially effects of intermittent catchment glaciation. We've kind of been able to rule this one out. So we do know that there has been some glaciation in some of these catchments. Some of the sediment is derived from the rains. But we're looking at something like 8, 9, 10 fan systems here, and they've all been glaciated to a different extent. And what we see is that this is just the 1800 record again, that's the grain size. And the moraines are quite coarse, right? Landslides into the catchment, that's their grain size too, they're a bit less coarse. So what we see is that certainly when it gets warmer, the grain size on the fan is moving towards these sediment sources. So they must play a role. But, it's all very well having a source of sediment. You've got to be able to transport it. If you can't move it, it's not going anywhere. And of course, the area of these moraines is quite small compared to the size of the Holocene deposits. And we're pretty sure this is glacial because it's really coarse today. It's not. It's not just a sort of export at the end of the last glaciation period. Now, one thing we do see, however, is that this is the grain size and this is sea surface temperature. What we do see is that the grain size of export increases predictably as a power law function with increasing sea surface temperatures off the coast of Santa Barbara. Why does that matter? Because all of the moisture in the Sierra Nevada comes from the ocean off the coast of California. And we know that sea surface temperatures are directly correlated with storminess. In fact, it's really wet in California at the moment, and that's because sea surface temperatures are at 2.5 degrees warmer than they normally are due to El Nino. So this could be a storminess effect. And in fact, the last big event on this fan, the Oak Creek event in 2008, was actually driven by some giant storm cell that was actually generating 30 millimeters of rain an hour. I mean, this is fast, right? 30 millimeters of rain in an hour. The mean annual precipitation in the town of Bishop up the road is only 148 millimeters in the entire year. So this is really going for it. So that destroyed 25 homes, or as the Los Angeles Times put it, mud boulders destroy a fish hatchery. I think I've felt sorry for these people. But the fish farm was apparently historic. So, a storminess effect would be a really interesting way of generating this, because today it's dry, but when it does rain, it really goes for it. At the last glacial maximum, it was on average wetter, but perhaps it was more drizzly, if we put it that way. And certainly when we look at the size of these channels, this is the flow width of these channels we've measured, they're certainly bigger and more variable into the Holocene. And actually, those flow widths, so this is age, flow width, these are our measurements. There's a lot, the error bars, I'm being honest on here, I'm putting big error bars on because those error bars are big. But in general, the size of these flows increases with sea surface temperatures, and you could read that as storminess, if you like. So, I think in this system, at least, we're recording climate change with high fidelity, and that might be due to increased storminess driving larger and more coarse flows into the Holocene. Right, I'm coming to the end of my hour, so I think it's time to wrap up. And I want to give you some perspectives on what I've just talked about. I do not think that we should be surprised that it's hard to decode geomorphic or stratigraphic systems for tectonics and climate in a quantitative way. The Earth's surface is complex. I think that good studies use both observation and modeling. And I think that there's value in having modeling that is relatively simple to start with. I think that if you build a very, very complicated model, you end up demanding a whole bunch of inputs that for the geologic past we do not know. I think in terms of landscape response to tectonics, we've done quite well at understanding that. And there's been a real sea change in the last 10, 20 years. I'd love to see more data sets to address the key question of whether or not stratigraphy records climate, because we always assume that it does. And in terms of geochemistry, we've done quite well with this. In terms of physical grain size sets, well, we've done that qualitatively. I'm interested in doing it quantitatively. And because this is hard, we need to choose our field sites well. But at least for some of this new data, and it's been fun to work on some new work, alluvial fans in southwest USA, they do seem to show that they record climate in physical stratigraphy with exceptional fidelity in some circumstances. So thank you very much.
Well, thank you very much, Alex, for that fantastic introduction to a very big challenge, as we said at the beginning. A challenge which you and your colleagues are starting out on, I think. So, who has a question? There are a couple of roving microphones, so please wait for them to arrive with you. Georgina, let's start with the gentleman down here.
Thank you for a very interesting talk. I hate to ask you a question about something you didn't talk about, but
yeah,
bear with me. One thing you didn't talk about was vegetation cover and soil management and human interactions with all these processes. Is that something that you look at, or someone else?
Yeah, so vegetation is really important. I think that we know that vegetation and climate change are inextricably linked. And actually, when you, for some of those examples I showed you in the southwest of the USA, there's also the time that we see a changeover in the flora from juniper, basically, to this sort of scrubland. And that makes a role, and I think ecologically, geomorphologists are really working on that problem. I think that one of the big challenges at the moment is that we're not entirely sure how to parameterize how vegetation affects erosion rates. I mean, I've got a colleague, T.C. Hales in Cardiff, who works on soil stability and root density and things like this. So people are working on it, but we are still not very good at solving that problem. But I think that you're correct to highlight that that's a real issue. In terms of human effects, well, I suppose here I was mostly interested in the tectonic and climate effects over the long term. You know, clearly humans have become a major agent of change on our planet. I've got one of my students is working out in the Gulf of Corinth, and you know, we know that Leonidas held off the Persian hordes under Xerxes at the gates of Thermopylae that were allegedly 10 men wide. Well, now that whole bay is filled into like 2 kilometers wide. And that's mostly driven by tree loss in the last 300 years. So that also is a big issue. You know, it's almost to me like a separate research challenge, but you're quite right to highlight that as an important factor.
There's a question down towards the front. Could you wait for the microphone to reach you?
With the large amount of work you've done, obviously that's a template and there'll be a lot of fine-tuning to do in decades to come, I would think.
There definitely will.
Are you, I don't mean are you, is it the idea to proceed further or to also go to another geographic location to try and confirm some of the data that the plots that you've shown there equally relevant?
Yeah, that's a good question. Clearly, we want to explore this in a range of areas. What are the circumstances? So I presented some field data that show that kind of sediment routing system, governed by a particular type of erosional dynamics, is sensitive to interglacial climate change, particularly in an area where we've had big changes in the storminess over time. Now, if we went somewhere else, we might have different long-term erosional dynamics, and we might have a different climate signature, and we might have a different sensitivity of the landscape. It's almost like we need to map in the n-dimensional space of sensitivity and response. So I've got a couple of PhD students trying to do just that. We've got some examples that we've been working on in Cyprus and in Greece.
There's a question right in the middle of this plot and then another one down the front.
Yes, another control on the grain size of the sediment is surely the nature of the source rock itself.
Yes.
Which you don't seem to have talked about apart from the Owens Valley where it was uniform.
Yes.
So that's going to be a how do you model that in?
So that's a really good question. So how lithology controls source grain size really matters. And so we have to think about what is the kind of grain size that's sourced if we just fragment rock of different type compared to what you get when, for example, you get shallow or bedrock landsliding, when you've got different soil production or regolith erosion rates. That really matters because the sediment transport system moves the grain size distribution it's provided with. So in fact, one of my PhD students, Spanish PhD student, Duna, she's coming tonight. Her whole PhD is all about how does the grain size distribution of source sediment change along the strike of faults? Because as you rightly highlight, that's an important constraint. I mean, in the theoretical example, if I took a truck of gravel that someone had sieved down to, so it's all like 1 centimetre in size, and I dumped it in the top of a river, then we wouldn't have any grain size variation for the fluvial system to work on at all. So it clearly matters.
I was going to ask the same question, so I had to think up a new one. But,
Good.
Having read geophysics at Imperial, I'm probably not even allowed to ask a question.
Go for it.
Pre-Cambrian. But the question is, I think you raised it right at the very beginning, the working back. So your petroleum geologist goes into the field, and he's measuring all these grain sizes. I can't quite see how he can work back through all this complicated. You're working through the chain that way, but the practical field geologist, he's got to work back the other way. I just wondered if, having worked on a lot of alluvial fans, you know, they all look the same to me in a way, but how you can get back to trying to understand the fault patterns and the things that led to that erosion.
Okay, so that's one of my main motivations, is to think to what extent can we invert the stratigraphic record either in terms of volumes or in terms of grain size for what's going on at the time. And I think that for the system I presented you here, if you go and measure a whole bunch of grain sizes, then actually, because there's a one-to-one link between your paleoclimate proxy, you do quite well in terms of getting a reconstruction. For other systems, you wouldn't do very well at all. And I think it's important to accept that I think that there's a danger of saying, oh, well, I'm going to go, I work on a lot of stratigraphy. You go, you measure some stuff, and you go, right, this is, for instance, my rift climax. I was chatting to a bunch of colleagues, Howard Johnson, actually, about some stuff in Suez. And, it's very tempting to be like, okay, that's when all the coarse sediment comes in, right? I'm going to say that's the time of my rift climax. But actually, it's not at all. The rift climax is actually lower in the stratigraphy, and that's when everything goes really fine, because that was the moment in which tectonic rates sped up, but the landscape was yet to respond. So I think that I am not sure that we're at the stage of having a full quantitative inversion of stratigraphy for tectonics and climate. That's the holy grail, if you like. But what this kind of work has done is given us some thought experiments and a different way of thinking about the kinds of questions we might ask when we go to the field. So I'm not trying to say to you that I have all of the answers. That would be a type of megalomania that I am going to shy away from for now.
Any more questions? One more question. Thank you, sir.
It seemed to me that most of what you talked about was, if you like, waterborne, whether it was glacial or riverine. But surely there's also, for the very lighter grains, dust, wind erosion. And that doesn't seem to have entered your calculations.
So clearly the wind part does make a difference. Wind selects pretty carefully in terms of its grain size. I will clearly and honestly say that I haven't been working on aeolian systems, and what I presented here doesn't address that problem. I think that when you look at if I think of the work that my PhD student who I mentioned before, who's working on sediment sourcing, is doing, the proportion of grain sizes that I think disappear from most systems due to wind, or at least the ones I'm working on here, is relatively small. That's not to say there aren't desert systems in which it's the predominant form of sediment transport. So I haven't worked or integrated wind into this. If you have some suggestions about how that would be done, I'd love to hear from you.
I'm thinking of the huge lowest.
Yeah, no, so if you go to China or Mongolia, then of course, and that's a huge, I was listening to a talk about that quite recently. So I'm not, again, if you wanted to look at the wind issue, that is another avenue to explore. This is not a template for every single method of moving sediment on planet Earth.
Well, thank you very much. Alex is going to have to give this lecture all over again to a fresh audience this evening, so I think we should let him go at this point. Thank you all for your probing questions, which I thought were excellent, and to Alex for answering them. And thank you again, Alex, for a fantastic talk.
Thank you.